All right, we're going to talk about something called oxidation numbers. And in order to find out kind of what they are and to give you a brief introduction of what we use oxidation numbers for, I want you to turn to your book, page 232. And I want you to read that first paragraph on oxidation numbers. 232, oxidation numbers. All right, so when we've been looking at elements, we've been given us a specific charge on an element, okay? And what the charge tells us is its distribution of electrons around that particular single element, okay? And when we start looking at compounds now, we've got different distributions of electrons within that compound, okay? So what oxidation numbers tell us is it tells us the distribution of electrons among atoms in a compound. All right, so I'm going to give you a quick example here. We haven't gone through chapter 6 yet, which is building what we call Lewis structures. Okay, but this is the Lewis structure of a water molecule. Okay, we haven't gotten to this part yet, but I want to show you the charge distribution and how oxidation numbers kind of play into this. So water is a covalent compound in which they share electrons, okay? So here we've got an oxygen atom bonded to two hydrogen atoms. What do we know the overall charge is of a water molecule? Does a water molecule have an overall charge? No. Overall, the charge of our molecule is neutral, right? So overall, we've got a zero charge. However, within this molecule, electrons are not distributed evenly. Okay, when these molecules share electrons or they transfer electrons between atoms, they're not shared evenly. Okay, so what happens in this is a bond, this is a bond, and we've got an electron shared from each of those. However, the electrons are shared more towards oxygen. Okay, oxygen starts to kind of hog those electrons, and that has to do with its electronegativity and all that stuff that we'll get into eventually later. But since these electrons are not shared evenly, they're not distributed evenly within this molecule, that leaves us with essentially a plus charge on each hydrogen and essentially a -2 charge on our oxygen. Okay? So, although our molecule has an overall charge of 0, each of these elements takes on kind of a mini charge or a partial charge, and that's what we consider its oxidation number. Okay, so that's kind of just a general, very, very brief introduction to the Lewis structures and what they look like. But essentially, even though we've got a neutral molecule, it doesn't mean that electrons are distributed evenly throughout that molecule. Okay, so these oxidation numbers tell us kind of where the electrons are located depending on our position within our molecule. Does that kind of make sense? Okay. Here's our rules for oxidation numbers. Okay. First rule. Elemental compounds always have an oxidation number of 0. Okay, and what we say when we mean elemental compounds is when we have a single element, if we have an element bonded with itself, things like that. Those are elemental compounds. They have an oxidation number of 0. So if I ask you for the oxidation number of sulfur, you're going to tell me 0. Okay? Of just by itself, an element has an oxidation number of 0. Okay, so that's the easy one. Now we've got some certain elements that take on an oxidation number always. They kind of get to keep their charge as their oxidation number. And that depends on their electronegativity, how badly they want to take electrons from other atoms. Okay, so fluorine always has an oxidation number of -1. Okay. Fluorine always has an oxidation number of -1. It always gets to keep its true charge when it's in a compound. It always gets to keep its true charge as its oxidation number. Okay, and it's because fluorine wants electrons more than any other element on the periodic table. So it's always going to have those electrons shaded towards its direction. Okay, so if I give you the molecule NaF, and I'm asking you to find the oxidation numbers of each element in our molecule, we know that overall this molecule has a charge of 0. So that means our oxidation numbers need to add up to 0. We know that fluorine gets to keep a -1 oxidation number because that's what our rule just says. Fluorine always has an oxidation number of -1, which means sodium's oxidation number must be +1, okay, because we want our overall to be 0. So oxidation numbers are similar to charges, but they don't always match the charge we can see from the periodic table. Okay, not always. All right, so there's our rule with fluorine. Next is oxygen. Oxygen has an oxidation number of -2, except when paired with fluorine. Okay, oxidation number of oxygen is always -2 unless it's paired with fluorine. Okay, if it's paired with fluorine, then it takes on a +2 oxidation number. Okay, so if it's paired with fluorine, that's the only exception. If it's paired with fluorine, it takes on a +2. Otherwise, if it's paired with anything else, it gets its -2. It gets to keep its regular charge as its oxidation number. Okay. All right. Next is hydrogen. This is our last elemental kind of exception here. Hydrogen has an oxidation number of +1. But here's our exception. So except when paired with a metal then it has an oxidation number of -1. Oops, I ran out of room. Okay, so hydrogen has an oxidation number of +1 except when it's paired with the metal, then it has an oxidation number of -1. Okay, so those are our 3 elemental exceptions. And those 3 are always true. Questions so far? Okay, let's keep going. We have 2 more rules, 3 more rules maybe. Okay. Oxidation numbers must add up to 0 in a neutral compound. Okay, so anytime we have a neutral compound, we have to make sure that our oxidation numbers add up to 0, just like our charges would normally add up to 0. Okay, the same is true for charged molecules. Oxidation numbers must add up to the correct charge in an ion. Okay, remember an ion is any charged particle. So if we've got a compound that has a charge, that means our oxidation numbers need to add up to that particular charge. Okay, if our charged molecule is -2, our oxidation numbers have to add up to -2. Okay, so the most electronegative element gets to keep its charge as its oxidation. Take a look at the electronegativity scale I just gave to you. This is called the Pauling scale. And what it does is that you see this fluorine is really dark, and it spreads lighter as you go down and to the left. Okay, so here's a rough periodic table here. Okay, and fluorine is over here, really on the top right. Fluorine is what we consider the most electronegative element there is. And when we talk about electronegativity, what electronegativity means is essentially how badly an element wants to take electrons from someone else. Okay? And if we think about fluorine's electron shells, how many valence electrons does fluorine have? How many valence electrons? 7. It has 7 valence electrons. It's in group 7, which means it has 7 valence electrons. How many electrons does it want to complete its octet to be happy?
8.
It wants to have 8, so it needs to take 1 electron from someone else. That's it. It only needs 1 electron. Okay, and those electrons right now are as close to the nucleus as it can get. So it really, really, really wants to complete that octet. Okay, it wants that electron more than any other element on the periodic table. So it's considered the most electronegative. Okay, and then as we go down and to the left, we see a decrease in electronegativity. That means francium doesn't want electrons at all, right? Francium's the bottom left. Can we see its electronegativity value?
Yeah.
What is it?
It's
0.7. And fluorine's is like 4.19, right? 4 point something? 3.9, sorry. 3.9. So it's a big difference between those two. Francium does not want electrons. It would rather give up its 1 electron that it has in its valence shell than to take another one, right? It's going to give up one a lot easier than it's going to take it. So fluorine is the most electronegative. So when we look at our last rule for oxidation numbers, that our most electronegative atom gets to keep its charge, that's the chart you look at. That's the chart that helps you decide. So essentially the element closer to fluorine gets to keep its charge. Okay? But some of them are kind of close in proximity, right? Do you pick nitrogen or sulfur? You have to look at their values. Okay?
So, what?
All right, I know this seems a little bit foreign right now, but I promise we'll get there. Okay? So we're going to find our oxidation numbers of this molecule. Let me move it down just a little bit. UF6. Okay, so let's go ahead and follow our rules, and I'll show you kind of how I decipher these problems. All right, we know that fluorine's oxidation number has to be what? It has to be a -1, right? So I usually put that oxidation number up top. I know there's 6 of those fluorine molecules. So that means overall I've got a -6 that I've got to balance here. Okay, overall, what do I want my charge of my molecule to be? Neutral. So that means I want my oxidation numbers to add up to 0. Okay, if I have a -6 here, what needs to go here? +6. How many of these molecules do I have? Only 1. That means my oxidation number of that molecule must be +6. Okay, so the way that I kind of decipher these is I put my totals down on the bottom, and I put that element's oxidation number up on the top. You can do whatever works for you best, but that's kind of how I decipher myself through these types of problems. Okay? Oxidation numbers, you tell me F has an oxidation number of -1, uranium has an oxidation number of +6. Okay? And really, I'm okay if you circle them up top or something like that, if it doesn't give you space to write them out to the side. Okay, but remember that these totals down here at the bottom are not our oxidation numbers. It's our individual atom-based oxidation numbers. Okay, so it's per each atom. All right, let's try another one. Let's try H2SO4. First thing I want you to do is name this molecule. First of all, is it ionic, covalent, or an acid?
Ionic.
What's our clue when H's comes first?
Oh, acid.
It's an acid. Okay, it's an acid. We need to do some review before our quiz next time. Okay, it's an acid. This anion is called what? Sulfate. Okay, so now we can look at our little acid cheat sheet, and we know that this is called sulfuric acid. Okay, H comes first, hydrogen comes first. That's our clue that it's an acid. Then we look at what polyatomic ion or what anion it comes from. This happens to be an 8 anion, which means our acid ends in ic, acid. Okay, I know it's been a couple days since we've done it, but that's what our quiz is over next time. Ionic, covalence, and acids. So this is sulfuric acid. Let's go ahead and look at our oxidation numbers here. What do we know oxygen always has an oxidation number of? Oxygen always has -2. And there's how many of those oxygen atoms here? 4. So that means total down here we have a -8. Okay. Then we'll work our way over to hydrogen. Okay, because sulfur is kind of our in-between guy here. We don't really know about sulfur, but we know about oxygen and we know about hydrogen for sure. So hydrogen's oxidation number is always +1. Okay. And there's how many of those guys? That means we've got a +2, we've got a -8, and what do we want this whole atom to add up, this whole molecule to add up to?
0.
We want it to add up to 0. Okay, which means what needs to fit here for sulfur?
6.
+6. Okay, and how many sulfur atoms do we have? 1, which means that singular sulfur atom has to have an oxidation number of +6. Okay. Again, you don't have to follow this exact notation like I do with things on the top and things on the bottom. That's just kind of how I work through it. You don't have to follow that system. If you find something that works better for you, that's fine. Okay, but our overall oxidation numbers here would be hydrogen has an oxidation number of +1, sulfur has an oxidation number of +6, and oxygen has an oxidation number of -2. All right. ClO3 minus. ClO3. I also need to make the clarification that this is Cl, chlorine. I had some of you on your quizzes say CiO3, right? This is an L because it's chlorine and chlorate, all that kind of stuff. Okay. All right. Just a clarification. So what's the name of this molecule right here? Chlorate. Right? So, which molecule should we start with here? We should start with oxygen, since we know oxygen's oxidation number is always -2, which means the total for that those oxygen atoms has to be. Okay, now here's where the change comes in. Our overall charge on the molecule is -1, which means we want this bottom to add up to -1, right? -1. Since our overall compound has a charge, we want our oxidation numbers to add up to that charge. Okay, which means what number needs to go here?
A 6.
A +5, because we want it to add up to -1, not 0. Okay, and how many chlorine atoms do we have in this molecule? 1, so that means our oxidation number for chlorine is just +5. So Cl has an oxidation number of +5, and oxygen has an oxidation number of -2. Okay. Questions here? All right, I want to try one more. That's going to change that first one just a little bit. N2O5. Let's name that molecule first. Dinitrogen. What? pentoxide. And it's ionic or covalent? It's covalent. Good. All right. So what do we know about oxygen? -2, which down on the bottom for our total gives us. All right, we want this to add up to 0. So what do we need here for our total for nitrogen? We need +10 to be our total, but we have 2 nitrogen atoms. So what's that mean the oxidation number for a single nitrogen atom must be? +5. All right, very good. I want to see where that, if you have a subscript on your first one, you've got to make sure you divide this total by your subscript to get to your singular oxidation number. So N has an oxidation number of +5. Oxygen is -2.